Hi everyone, I am Mohit Agrawal, a PhD student at Georgia Tech. I am working with Dr. Raghupati Sivakumar. I'll be presenting our work on Charge for a Whole Day, Extending Battery Life for BCI Wearables using a lightweight wake-up command. The wearable interfaces have become quite pervasive, with almost everyone wearing fitness trackers or smartwatches. Similarly, there are a handful of commercial BCI headsets available in the market used for entertainment, education, or meditation purposes. Despite this, BCI wearables are nowhere close to the other wearables in terms of their adoption rate, and it is important to look at one reason that could be stalling it. In a study conducted to assess the primary concerns of the users with the wearable technology, battery life was found as one of the most prominent factors for user dissatisfaction. For a relatively simple BCI wearable OpenBCI, it has a battery life of only 3.5 hours. We plot in this figure battery life of major BCI wearables with their battery capacity as a proxy of their form factor. In the bottom right corner, for the reference purposes, we have the Apple Watch and we can see the battery life of BCI wearables is significantly short in spite of having higher battery capacities. For example, battery life of Mindwave is 8 hours, but the battery capacity is 4 times than the battery capacity of Apple Watch. This degrades the user experience by requiring the headset to be charged multiple times a day. We investigate the question why the battery life of BCI wearables is so short. We concluded that since sophisticated ML algorithms are required to process EEG data, which resource constrained BCI wearables cannot support in real time, BCI wearables need to continuously sense and ship the raw EEG data. This continuous sense and ship model drains the battery life for BCI wearables. An approach to save battery life is the design of a wake up command, in which the device is turned to low power mode when user is not actively using it, and switched to high power mode when the user wants to use and wakes up the device by initiating a wake up command. For example, Hey Alexa, OK Google, and Hey Siri are some wake up commands for the commercially available voice interfaces. One of the interesting things about these interfaces is that the wake up command is the same modality as of the regular command. However, since they are always connected to a power source, the implications on battery life is insignificant. More similar to our case is the wake up command design for smartwatches, where in low power mode we turn off the components like GPS or backlight screen, consuming significant power, and wake up the device by leveraging other modalities like physical tap or movement triggers. In BCI wearables, the challenge to design wake up design is twofold. First, there are not any obvious components like screen backlight or communication modules to turn off. So we have to identify the components that could be turned off or run in low power mode. Secondly, we would like to restrict ourselves to a modality which can be detected through EEG to allow ubiquitous use across different users, environments, and conditions. To identify which components of BCI wearable have a significant impact on its battery life, we performed a power consumption analysis on the OpenBCI wearable. OpenBCI is a portable, low-cost, and open-source wearable interface. BCI wearables in the consumer sector conform to a typical architecture, and we select OpenBCI as the representative example of them. We talked about the short battery life of OpenBCI before, lasting approximately 3.5 hours on wearable battery specifications. To identify the power consumption of each component inside OpenBCI board, we run a micropower analysis where we dissect the OpenBCI board to its individual components and calculate the power consumption of each component. Based on the datasheet specifications and reconfigurability, we select three components for further experimental analysis. These components are clock rate, ADC channels, and programmable gain. We perform a parameter sweep over all the possible reconfigurable parameters for these three components, and we conclude that out of these three components, clock rate and ADC channels in tandem consumes around 97% of the battery life, which means programmable gain is relatively insignificant. The second key insight was that there is a linear relationship of power consumed with these three components. Based on this linear relationship, we compute the current consumption at the lowest value of frequency, single ADC channel, and when the radio is turned off. And we concluded that the battery life extends from 3.5 hours to 10.14 hours, approximately a 3 times improvement. Now, the main challenge is to design and reliably detect a wake up command with a single EEG channel and in real time with low CPU frequency. Now we move to the next challenge of selecting the modality for the wake up command. Let us look at some trivial approaches for the wake up command detectable by EEG based BCI variables. A simple approach is closing the user eyes and the user going in the rest state. It invokes alpha waves and can be easily detected through EEG. However, the wake up command is not easy and inconspicuous to the users. A second approach could be presentation of an array of lights, flickering at the different frequencies, and the command can be detected by estimating the element of the array the user was attending to. Such an approach is dependent on an external stimulation which is not desirable. Motor imagery scenarios, for example, imagination of limb movements, are good examples of wake up command, however, are very difficult to detect without high computational learning systems. An appropriate command modality is one which humans do naturally, should not require any external stimulation, and the impact on the EEG should be pronounced enough to detect reliably in the resource constrained manner. We rely on iBlinks as the wake up command modality for our solution as it satisfies all of the above requirements, and in addition, it provides benefits which are no hardware modifications required on the BCI variables. It can be used in mobile scenarios where hands are occupied or cannot be used and is non-intrusive to the environment around the user. Now, we proceed to tackle the challenge of detecting the eye blink in the low power mode. Let's first look at how the eye blinks affect the EEG waveforms. On a voltage time plot, the eye blink waveform looks like a trough pattern, where the depth corresponds to the intensity of the blinks and the width corresponds to the duration of the blink. Inside an eye, cornea and retina are oppositely charged and hence produces an electric field when a blink is performed. This electric field interferes with the EEG and shows maximum activity over the frontal channels. To study the natural blinking patterns, we collected the dataset of 12 users and analyzed their blinking patterns while the subjects were watching a video or reading an article. As we know from our day-to-day experiences, the frequency of single blink is very high due to the natural blinking patterns and hence cannot be used to design a wake-up command. We also analyzed the blink duration and concluded that the blink duration is highly variable across users and user states. Hence, it is not a good wake-up command candidate as well. However, we found that multiple blinks, like 2 blinks or 3 blinks, are significantly less, as can be seen from the right figure, and hence can be leveraged to design our wake-up command. So we consider an array of multiple eye blinks as the candidate space for wake-up commands and analyze them in terms of their false positive rate and user comfort to select a default wake-up command. We define the natural FPR as the number of times the wake-up command will be issued without the user intent due to their natural blinking patterns. From the figure, we can see that for 2 blinks, the FPR is 30 per hour, which is quite high, but it dramatically reduces to 1.43 per hour for 3 blinks. From the user comfort study on 209 volunteers, the 3 blinks command was found to be slightly comfortable with an average comfort score of 3.7. Hence, we set the default wake up command to 3 blinks but allow an option to change the wake up command to k blinks later. Now we move on to discuss the algorithm to detect the wake up command in low power mode. We present TRANS, the wake up command detection algorithm, to detect a series of blinks in the EEG data. TRANS is built upon the robust noise handling and peak detection methodologies proposed in the signal processing literature. Details of the algorithm are presented in the paper. A core insight behind TRANS is that it leverages the fact that the issued wake-up command will always have 2 or more consecutive blinks. It allows TRANS to build the iBlink fingerprint in an online fashion without additional variabilities due to the user states. To evaluate the performance of the TRANS, we collected the data of 16 users and asked them to blink multiple times to issue the wake up command. A green plus marker was shown to guide the users to perform 2 sets of triple blinks, that is, 3 blinks followed by 3 blinks. Averaged over 16 users, TRANS performed with a recall of 0.89 and a precision of 0.99. The average F1 score obtained was 0.93. From the distribution curves, we can see that more than 80% of the users perform with at least 80% recall, signifying the robust detection capability of the TRANS algorithm. Since the TRANS algorithm is parameterized upon the number of blinks, we compare the recall and precision rates of the k blinks wake up command. The 2 blinks command has the highest recall of 0.95 with a precision of 0.98. Recall decreases with an increase in k. As for detecting a k-blink command, TRANS has to detect k-1 consecutive pairs of blinks accurately. To compute the false positive rate of the algorithm, we conducted the uncontrolled experimental study where the EEG of 12 subjects were recorded while they were watching a video or reading an article. We can see that natural false positive rate decreases significantly with 3 blinks due to the natural blinking patterns. The algorithm false positive rate decreases from 7.21 to 1.46 from 2 blinks to 3 blinks. To look at the trans solution through the lens of end user usability, we first investigate user comfortability with the proposed wake-up command. We performed an IRB compliant experimental survey where a Qualtrics questionnaire was prepared to rate the comfort level of different wake-up commands. Out of 188 valid responses, more than 78% participants said that the default wake-up command, that is 3 blinks, was not uncomfortable. This compares to the 96.6% of participants who did not find the 2 blinks command uncomfortable. The average user comfort score for 3 blinks was obtained as 3.68, somewhat less than slightly comfortable but considerably higher than neutral. We also measure the time taken by the users to deliver the command across all trials and subjects. A mean action time of 2.5 seconds was obtained. Large variability was observed across subjects. For instance, subject 10 took 1.47 seconds and while subject 14 took 3.31 seconds. Finally, to evaluate the power gains, we implement the trans algorithm on the OpenBCI board. For this experiment, we modify the OpenBCI architecture to run at 6 MHz and 2 electrodes and to receive raw EEG trace from the computer via RFDNO instead of the electrodes. The trace-based analysis enables the correct measurement and replication of results, which wouldn't have been possible if evaluated directly on the prototype. We measure the average current drawn during the experiment duration for different activity ratios and compare with the average current drawn in the absence of a solution. The figure shows the battery life of OpenBCI for various activity ratios. With the power experiments, the battery life for 2% activity ratio was found to be 9.3 hours, which is 2.7 times improvement over the non-trans solution. We also measured the latency of the command and non-command detection on the OpenBCI hardware in low power mode. It took an average of around 121 seconds to detect the presence of command and around 24 milliseconds to detect the absence of command. The quick blink detection in order of a few milliseconds enables the real-time operation without adding any detectable lag for users. To conclude, in this work, we first surveyed the commercially available BCI headsets to verify the problem of short battery life. We proposed a wake-up command detection strategy which enables always-on BCI platforms to run on low power mode and transition to active mode only when users issue the command, solving the problem of charging BCI headsets multiple times a day. We performed an experimental power analysis to find components to turn off or to set to lowest possible settings in the low power mode. We use iBlinks as the building blocks to solve the challenge of designing command and detection strategy under the resource constrained environment. Based on user characteristic analysis, we design a wake-up command for the BCI wearable headsets that balances the requirements of accuracy, false positive rates, and is comfortable for the users to use. We also presented the lightweight trans algorithm, and through extensive experimental user studies, we validate the performance of trans and show that trans can achieve around 2.7 times improvement in battery life. Thank you for your interest in our work. Please visit the following links for datasets and codes of the paper.